Hi, welcome to Nanotalks. This Nanotalk is a recording of a recent webinar in which we showed a new FIB lamella preparation process for in situ TEM and shared some best practices. This webinar was hosted by me, Olaf Weller, and the presentation was given by my colleague Jin Pivak, who has been leading the development of our new FIB stub. The presentation of Jin will last about 40 minutes, and then you can listen to the Q&A we held with the audience. So please enjoy this Nanotalk.
So hi everyone. I switched on my video for a bit just to introduce myself. So welcome to this webinar. So we're going to talk today about FIB stub, our new FIB stub, and the process, how to prepare FIB lamellas for in situ TEM experiments. And so I will switch it off, and we'll see you after during the Q&A session. So today we're going to do, in the coming 40 minutes, I'm going to give you a short introduction on the topic. I'm going to show you our new FIB stub and how, using this FIB stub, we can prepare lamella on a MEMS-based nanochip. I will discuss the main challenges during the sample preparation. Also, I will show best practices, the ways how you can overcome those challenges and improve the process in general. And I will finish with examples and a summary. So first of all, in this presentation, we're not going to talk about copper grids. So copper grids, well, the reason is we are not going to consider them. They are limiting your experimental capabilities. So we focus, and you see it here, on the MEMS-based nanochips, and we use them as sample carriers. So why we're interested in nanochips? Well, first of all, nanochips can be functionalized, which means we can manipulate the environment around the sample, and we can use them to do in situ experiments. So what kind of in situ experiments we can do? So we can do in situ heating, we can do in situ biasing, or we can do in situ heating and biasing. So here you see the examples of nanochips for geol TM. So the size of this geol nanochip is 4 by 10 millimeters, so it's pretty large and it's easy to handle. The main functional part is here in the center of the nanochip. So if I zoom in, here you see a suspended silicon nitride membrane, and in the center of the membrane you have the main the active element. The active element in this case, this is a heater. Inside the heater you have, which you see black dots, these are the electron transparent windows where the sample needs to be positioned. So in this case heating is done very locally. If we consider heating and biasing chip, you see the same, more or less the same structure. We have silicon nitride membrane, we have here a heater, and we have here biasing electrodes. Just because the stimuli application happens locally, so the stimuli is applied very locally to the sample, nanochips are characterized by great sample stability. You can also apply, you can heat up to very high temperatures. You can apply extreme electric field voltages. The heating and cooling is done instantly. And as also shown here, you can combine different stimuli together, which is heating and biasing. On top of that, you can add probably another stimuli to expand the application space. So we have nanochips for heating and biasing. So where we can apply this? So the application space, or you can apply to various research fields. So you can, for example, study semiconductors and investigate the degradation behavior in transistors. You can study resistive switching materials or phase change phenomena in this novel non-volatile memory. You can try to drive domains using either electric field or temperature in piezoelectrics and ferroelectrics. You can study performance of solar cells, either silicon or perovskite based. You can do solid-state electrochemistry and study cycling behavior of batteries and fuel cells. You can investigate the performance of LEDs. You can maybe study sintering of ceramics. And you can also study metals and alloys, either the defect chemistry, alloying, electromigration, various phenomena. From the practical application of view, the sample must be in a solid state form to run those experiments. And on top of that, it should be cut out from a specific place or from a bulk sample. And the FIB is the obvious choice to prepare the sample. So to run those in situ experiments, we need to prepare a FIB lamella on a nanochip. But for many people, it's something new. So where to start? How to approach it? So in a conventional approach, if you want to prepare a lamella on the nanochip, you use an OmniGrid. So I'm going to explain you briefly the process. So in the process, you take an SEM stub, you fix sample and a nanochip using a carbon tape to the SEM stub, and the sample and nanochip is positioned parallel. So you prepare a lamella, then you do a lift out. The lift out is done perpendicular to the surface. Afterwards, the lamella is being transferred to the OmniGrid, and well, you weld the lamella, you release the manipulator, and at this stage you melt down the lamella to desired thickness of 100 nanometers or less. After this step, since the sample is prepared, you need to transfer it from this point to the nanochip. But in this geometry, it's simply impossible. In this case, the lamella will land perpendicular to the surface of the nanochip, while we need to be parallel. So the way out is, which happens in majority of the cases, you need to open the chamber of your FIB. You need manually to rotate the OmniGrid 90 degrees to have the right orientation. So from here, what you do, you insert the manipulator, you weld it to the lamella, you unweld it from the OmniGrid, and then from this you can transfer it to the nanochip. So there are a few issues with the current approach. First of all, it requires an additional vent of your FIB, which makes the whole process more time-consuming. And secondly, just because the welding and unwelding here happens after the sample being prepared, the sample might be contaminated with platinum. So now we're moving to our new FIB stub. So our approach to prepare FIB lamella is slightly different. So we use so-called FIB stub. So this FIB stub, you can see it here. So the FIB stub is basically modified SEM stub that on the FIB stub you can put both the sample and the chip at the same time, and the aim is to facilitate the sample preparation. So what we have here, we have a flat side where you put the sample. Having the flat geometry makes it advantageous for the user, because any FIB operator works in a flat geometry. So everyone will know how to do at least the first part of the sample preparation process. So we have also two sides, 45 degrees. On those sides, we can put chips, nanochips. So this FIB stub is compatible with all double tilt chips for heating, for biasing, or heating biasing. On top of that, it can also be used with single tilt heating chips. So the FIB stub can be, it's compatible with Thermo Fisher or FEI and Joule FIBs, and the rest of the FIBs, they still to come. So what else do we have? We have a special pocket to position nanochip, and we have metal clamps to fix the chip in place. and also to ground it to avoid grounding in the FIB during the process. So we have a really nice and smart clamping mechanism, which makes the chip loading and unloading very easy. So I will show you the video, how it's done. So you take the chip, put it inside the pocket, slide it till the end stop, fix it. If you want to take the chip out, you release the screw, slide it back, and take the chip out. So as I mentioned, the process is very simple to load and unload Nano-Chip. And secondly, you don't need to use any more carbon sticky tape to fix the chip, which makes the process cleaner. So how we doing the sample preparation using the FIB stub? So in the following animation, I'm going to explain in detail the whole process. So we put the sample on the FIB stub, we put the Nano-Chip, we vent the chamber of the FIB, put it inside, pump it. So the first part is what I mentioned. Because of the flat geometry of the FIB stub, you need to apply the well-known process. Basically everything you know, you can just apply your knowledge here. So first what you do, you find the sample, put the working distance, write the working distance, the eccentric height. If you need, you put electron beam platinum. If not, you tilt the stage to be perpendicular to the ion beam and make the ion beam deposition of the protection layer, which is mostly platinum. Afterwards, you make trenches. You can do it either one by one, or you can do it together with small tilts or without. It depends on your own preference. Afterwards, you polish the lamella a bit after the rough cutting. You go back to zero tilt and make the undercut. So you can see here. You insert the manipulator and the GIS. You approach the lamella, you do the welding. You make the final cut to release the lamella. And then you do the lift out. So one important part is to mention, so the lamella, the Nano-Chip and the sample, their positions, their eccentric height is very similar, which makes the whole process safer. So in the next step, from the sample, you move to the Nano-Chip. So you adjust slightly your eccentric height, and then you tilt nearly parallel to the electron beam. So the next step is to put the manipulator in with the lamella. And as you can see, we don't put the lamella parallel to the Nano-Chip. We put it to a slight angle of 9 to 10 degrees. And the reason for that is to be able to mill the lamella from both sides. So when you have the lamella next to the surface, you make a weld, you release the manipulator, you take out the GIS and the manipulator, tilt the stage back to 0 degrees, rotate it. So here you see our sample area with lamella. Then during the next step, you tilt the lamella parallel to the ion beam. Well, not lamella, sorry, Nano-Chip. To have lamella parallel to the ion beam. And the next process, actually, you can use the same process you're using with Omni grids. So what you do, you at 30 kV use relatively high currents and small tilts to mill it down to 100 to 200 nanometers. Then you reduce the accelerating voltage to 5 kV. And then as a final step, use 1 to 2 kV in a larger angle to polish the sample to remove the amorphous layer. And when you have the desired thickness and the quality, you basically stop the process. So there are a few advantages of this process. Well, first of all, it's in this process, the lamella preparation is done in one step. You don't need to break the vacuum. And another reason is we do the direct milling on the chip, which means we will avoid any platinum contamination or any contamination while that can come during welding or cutting or whatever. And this is just one to show you as an example of the lamella quality you can achieve using this approach. So this lamella was prepared at Technical University Darmstadt by Alexander Zindler and Leopoldo Molina Luna. So this is lamella prepared on the nanochip. So if you zoom in on this interface and then you zoom in further, so you can see, so this is STEM HADF and ADF images, many images taken across the interface, stitched together. So with some practice, this is the quality you can achieve. And most importantly, let's say having the possibility to having the means and the procedure to prepare samples allows the user to focus specifically on the experiment and not solving the issues with the sample preparation. So we go into main challenges. So the first main challenge is device should be operational. So and here I should explain a bit. When we, for in situ experiments, let's say many of our samples, this is not a single phase materials, but it's actually a devices. So in order to study the device, to see its its dynamic behavior, the device should be operational. And this is especially important for biasing and heating and biasing applications and chips and samples. One of the issues that can prevent user to be able to measure the device is so-called short circuits. So in order to measure the property of your sample, there should be no short circuits on your chip. So here you see the schematics of the heating and biasing chip, and this is our sample area. So here you see an FIB image of the same sample area. So we have 4 biasing electrodes. Around here we have a heater. This is a lamella welded with platinum to the nanochip. And as you can see, we have platinum contamination, so-called platinum halo, around the lamella. And also it extends from one electrode to the other. If we apply a voltage bias to it, then basically the current will go, instead of going through your sample, it will go via the least resistive path. So basically it will go via platinum contamination. In this case, you will not be able to measure your sample. Another example is if you have the same lamella and you prepare lamella, you make 2 contacts with the biasing electrodes, and you apply again voltage bias. But here we have a platinum protection layer, and then if your sample is more resistive than the platinum protection layer, the current again will go via this layer, and you will not be able to measure your sample. You'll measure something else. Another limitation concerns the path of the electrical current. Basically, when you measure a device, quite often it's a heterostructure. And for heterostructures to be able to use them, the current needs to go perpendicular to the interface. However, if you don't do anything, you will be measuring the individual layers. So as you can see, if you don't do any additional steps, if you apply voltage to it, the current will be going through the individual layers. And in this case, so this is an example of phase change material. Heterostructure, you see different layers here. You will not be able to switch the material from crystalline phase to amorphous and vice versa. The last part is basically we need to avoid generating high currents or joule heating. For example, if you're looking to study the effect of electric field on a sample, but the sample is prepared to measure current, so you have two welding points, it means while ramping up the voltage or electric field, you will generate a lot of current in your sample, which means that instead of seeing the effect of electric field, you will see the effect of joule heating on your sample. So the issue with all those challenges, if the sample preparation is not done properly, you will lose TEM time and FIB time. So how it works? So you prepare your sample. Afterwards, you will take it to the TEM, and you assemble the system, and you will try to measure. If the sample is not prepared properly, you will not see the effect you're looking for. What you will do next? You will go back to the FIB to try to improve the sample, and it might happen that you take this. Let's say it will take you a few iterations before you reach the desired results. And another issue is, that you let's say you might get unreliable experimental results. So, and then which will lead to that you will draw different conclusions, wrong conclusions from your experiment. So, moving to best practices. Basically, the idea here is to show a few examples how to overcome challenges and improve the process. So, first of all, is the deposition layer. First suggestion is, so you need to define the deposition layer in the, let's say, to a specific appropriate size for your experiment. So the lamella should be not too small, not to fit in the window. It's also should not be too large, not to spend additional time on milling and deposition. Specifically for heating experiments, if you suspect that your protection layer will interact with your sample, it's better to put an enhanced material in between the sample and the protection layer. For Weissen experiments, to avoid short circuits, instead of having platinum, tungsten, or iron, probably it's better to use non-conductive protection layer like silicon oxide. So next point is about lamella thickness. So here you see examples of relatively thick lamellas on biasing nanochip, and this is on a heating nanochip. And frankly speaking, you don't really need to prepare thick, let's say, lamellas thicker than one microns. So you don't need to prepare one to 2 micron thickness. And the issue is that you will increase the milling time on the chip, which will basically complicate the whole process. Instead, what you can do, you can reduce the lamella thickness down to 0.51 micron before the transfer. So here you see the heating chip, this is the manipulator, and this is the lamella transferred, which is pretty small. In this case, so the advantage is you don't need to use very high currents, first of all, and secondly, the process becomes simpler. And this is, you see the heating nanochip, the top view, and here you already prepared lamella, and you barely see any damages to the silicon nitride. So next point is how to overcome platinum contamination. So as I mentioned before, we need to avoid creating platinum contamination. So what's the solution? Solution is to make trenches in the silicon nitride membrane, because our silicon nitride membrane is just a support. So you have here, we have a heater around and biasing electrodes around. So making those trenches will not affect any functionality of the chip. And having those trenches will allow us to actually disconnect both electrodes. And in this case, we don't, let's say the current, if you apply a voltage bias, the current will go through your sample, but not via the platinum contamination. So this is another example of a sample, and then you see the cuts here. Another important point is when you transfer the lamella to the nanochip, before inserting the manipulator with the lamella and the GIS, it's a good habit to lower the stage down by 300-400 microns, then insert the manipulator and the GIS, and then you can put the stage up to reach the final eccentric height. This is more a safer operation. So the next point is how to position lamella on the nanochip. The positioning depends, of course, on the final aim of the experiment. So we have three cases. We have a heating case, we have a case for biasing and heating when you don't want to measure any current. And another case is biasing and heating when you may want to measure RT or IV data. So how you put the sample lamella on the heating chip? So this is the top view of a heating chip. Here you see the heating line. This is our silicon nitride here and the windows. So in this geometry, you would put lamella here on the windows. So to have a bit more distance from the lamella to the heating lines, not to damage them during the milling process. So this is a side view from an NCM image. So this basically lamella is prepared on one of the elongated oval shape windows. And it's if you're going to do the milling on the chip, so it's better to avoid placing the lamellas on the central windows. In this case, you might damage the heater. And of course, judging by the size of the window, the lamella length should be in the range of 12 to 15 microns. So for biasing and heating samples, where you don't want to actually measure any current, but instead you want to see the effect of electric field on the structure. For example, you want to study ferroelectric domains, or you want to see electric field assisted sintering, you can just weld the lamella on one side. Just because, well, you don't need to have the second electrode connected. And in this case, the lamella thickness can be just in the range of 10 to 12 microns to position it between the closest inner electrodes. For biasing and heating samples, when you're interested in IV measurement or RT measurement, you actually, what you can do, you can prepare lamella on the outer electrodes. And in this case, you do need to make two contacts with the biasing electrodes of the chip. So this sample is actually yttrium zirconia. It's oxygen ion conducting electrolyte for specifically our experiments, biasing experiments at high temperatures. Those samples, the length of those samples should be in the range of 20-25 micron. For biasing and heating samples, actually for any, let's say any samples, well, specifically, sorry, biasing heating, if you don't want to, if you, let's say, don't like to have lamella on the windows, on the existing windows, you can create actually your own window outside and put lamella there. As I mentioned before, our silicon nitride just a support, so it will not affect any functionality. So this example of hafnium oxide, it's a work again from Technical University Darmstadt. So the lamella, the window was milled here, the lamella was prepared on top of our existing biasing electrodes, and then a few electrodes were made with platinum deposition. So how to avoid, again, short circuit due to platinum protection layer? So one way to do this is to mill completely away the platinum, if it's possible. So in this case, you will not have any issues with the platinum short circuit. In case your sample is positioned too close to the surface, so you cannot remove the platinum completely, in this case, what you can do, you can make cuts cut through the platinum layer just to disconnect the platinum protection layer. So the final let's say, point is guiding the electrical current. So this example you've seen. So in order to measure the phase change material, we need to guide the electrical current. So how to do this is by making a cut. So this is example of GST. So if you look from the top, so you have various layers. In order to guide the current, you make two cuts on two sides. So, and then in this case, the current will go perpendicular to the interface. So if I will show another example, so we have one cut that cuts through the sample and the bottom electrode, but keeping the top electrode. And then, so the current will go here, but here we do another cut to prevent current going through the top layer. And we cut the top electrode and a part of the sample, leaving only just the bottom electrode. In this case, when you apply bias, the current go perpendicular to the interface, and you will see the effect that you want to see. Another point to mention, important point to mention, is if it's possible, it's good before sample preparation is to increase the layers, the top and bottom electrodes, the thickness of those layers. So first of all, it will simplify the process of cutting. It will make it more precise. And secondly, it will improve to reduce the joule heating when you will be doing your biasing experiments. So now we move into examples. Successful examples of sample preparation. So first one is done together with Technical University of Darmstadt, and it is about resistive switching. So this sample you've seen already. So it's a hafnium oxide. So here you see different layers. So it's hafnium oxide with bottom electrode titanium nitride, top platinum PVD. You have the sapphire and a top platinum electrode from FIB. So this is the TEM image. So if you zoom in, you see the structure, and if you apply a bias to it in order to switch your material, basically what you can do, you can do unipolar resistive switching inside the TEM. So basically black and red curve here, it's a set of reset curves of this FIB lamella. And actually what researchers found out that the behavior of FIB lamella is very similar to the bulk behavior. So which means we can, using lamellas, we can study bulk properties. So another example is also about resistive switching from Beijing University, but this is more here in the previous example, the aim was to study the, let's say, material that is practically used. Here is more a fundamental study of how resistive switching works exactly. So this is again lamella prepared on a nanochip. Here you can see cuts in your sample just to guide the current through the structure. This is schematics, how you see. So you have two biasing electrodes. You have heterostructure, different layers, and the cuts. So when you apply, then you do the IV characterization. So you apply bias and you measure current and see the resistance. And then what the researchers saw that while applying the voltage, at some point, the current drops, the sample becomes more resistive. And if you take images at different stages of this process, either at as prepared state, somewhere between around 0.8 volts, and then here in the switch state, well, first of all, you see that you can do atomic imaging with it. And secondly, from measuring the intensity profile at different stages, you can conclude, actually, you can observe the formation of oxygen vacancies inside the lattice. And of course, you can confirm that using EELs. And the final example here is about the solid-state battery. First of all, it's very challenging to make this, the solid-state battery on the nanochip. So researchers, again from Beijing University, they were able to prepare it on the nanochip, biasing nanochip, And then, well, the process is very difficult, time-consuming, but it is possible. So basically you have here you have here the full stack. You have basically the one electrode, the electrolyte, the lithium cobalt oxide electrode, and also welding points to the chip biasing electrodes. So what researchers were able to do, they were able to characterize the cathode material in the SP paired state. They were able to delithiate the lithium cobalt oxide, see the IV curve, and then they were also able to observe what happens to the structure when you remove lithium from it. So the structure transformed from a single phase to a polycrystalline phase with certain orientation of those crystallites. And that's the end of my, well, that's basically was my examples. And basically moving to the summary. So first of all, it's very, well, assembly preparation is a very important step, especially for in situ TEM experiments, just because there are additional requirements that is placed on the sample. And as I mentioned before, these samples quite often are devices that should work. Additionally, so basically having the right tools can facilitate and simplify the whole process. In this case, you don't have the bottleneck of making the sample or figuring out how to make the sample, but you can concentrate specifically on achieving your in situ results. And of course, there are various challenges towards high quality and working samples for in situ TEM. However, with the right approach, knowledge, and support, it is possible to achieve the desired results. And with this, I thank you for your attention. So I'm a bit ahead of time, but I think it's good we will have more time for the questions.
All right. Yes. Thank you very much, Jin, for a great presentation. And indeed, now we will go over to the questions of our audience. So first up, our first questionnaire was Vijay. So Vijay, are you there with us now?
Yeah, can you hear me?
Yeah, we can hear you.
Yes.
So welcome.
Thank you. Thanks for the presentation. It was really good. I was just wondering, with the sample on top of the stub, what's the maximum height of the sample that you can put on top of there and still achieve, an easy sort of sample prep? And how are you actually mounting the sample to that stub?
Yeah. So let's say usually when especially you're working with, let's say, many samples you work with, it's samples prepared by deposition. So they quite often this like you have a substrate and thin layers. So at least the stub was designed for the sample of the thickness of 2-3, let's say, millimeters. Or well, maybe slightly more, but it's let's say if you want to put there the let's say a few centimeters of the sample, the height of the sample a few centimeters, and you want to prepare it, that would be tricky.
Yeah, because we're often working with metals and bulk materials in our facility, so that was something that I was interested in. So yeah, it's something that we'd have to think about.
Yeah. Yes. So well, just to make basically the idea is, in order to make it safe for the operation, the essential height of the sample and the nanochip chip should be similar. So in this case, there are certain restrictions on the height of the sample as well. Yeah. So they should be probably cut. And the way to fix the chip, so you fix the sample to the FIB stub, then you can use actually the carbon sticky tape.
Yeah. What's the channel there underneath the sample for then?
Yeah, basically it's an opening for the membrane.
Yep. While I've still got the microphone, I might as well ask one more question. With the GSD material example you gave, do you know what kind of substrate they would have been using to have the conductivity through the substrate?
This I don't know. I think that well, basically you can have two kinds of substrate, either non-conductive or conductive. In this example, I don't remember exactly what was the substrate, but probably for those experiments, it's better to use a conductive substrate.
Yeah. Thank you.
Yep, sure.
Okay, so thank you very much. Next up is Elena. Elena, are you there?
Yes, can you hear me?
Yeah. We can hear you, so please go ahead.
Thank you. Thank you, Jim, for this nice presentation. It was very, very instructive. I have certain questions because I will. I'm working with different materials, and I believe the use of the stub is limited to certain chips, and I would like to know what is the limiting factor.
Okay.
Or which is what makes a chip compatible with the stub?
Well, the chip was, so if I show it, so the chip was designed for certain chips. So this chip, so you can work with the chips for double tilt systems for heating biasing or single tilt heating. So basically these are the chips that was meant to use with the stub. So
basically,
it depends on the size of the chip. So basically it's meant for a specific size of those chips.
okay, and do you think that you so it is possible to adapt the stub to different chips in the I mean in the future, if DENSsolutions is thinking to adapt the use of this stub, for example, to the nanocell?
Well, actually, yeah. So we are looking into that, but that should be then. I guess it'll be our next version of the FIB stub. But yeah, we're thinking about that.
Okay, that's
just those chips. So those chips, the nanocells, nanoreactors, they have larger size. So the approach is needs to be done slightly different. Well, basically, we need to modify the FIB stub to make it happen. Although, just for you to mention, we have an alternative approach, not using this stub, but using different stubs, and then you can prepare a lamella on the either or a nanocell or nanoreactor.
Oh, that is very interesting to know. I would love to know a little bit more about that.
Sure, just I don't know. You can send me an email, and I can well send you some additional information.
Okay, thank you. I will for sure.
Sure.
I have another question. So, how does the redeposition, I mean, from the final milling, affect the chip?
Well, usually, if I move somewhere down. So when we mill, we actually mill parallel to the specifically for biasing experiments. We can mill away just a silicon nitride, but silicon nitride is just a support for us. So it doesn't have any function of heating or biasing, whatever. So if we mill away the silicon nitride, it will not affect the functionality of the chip.
Okay. So, and then you already mentioned that it's possible to make some trenches in the silicon nitride window,
Yes,
and
yes.
it will not affect the functionality.
No, let me see. I'm looking for an image. Well, something like this. Yeah, so basically what you see here, this is a window, and this is actually when the lamella was milled, then we milled away part of the silicon nitride. But again, the silicon nitride is just a support. It supports the rest of the structures and the lamella. And all the heating and biasing happens in a different place, basically. So it is possible to make trenches and cut silicon nitride, and it will not affect the functionality.
Okay. Okay. And I have a final question, very short. So,
sure, well,
do you think
we have time?
I don't want to monopolize the Q&A, but do you think it will be possible to use the system, I mean, both stub and chips in cryo conditions in the future?
I'm pretty sure yes. I don't see it, at least right now, I don't see any reason why not.
So in principle, you don't see any kind of limitation?
But you mean in the cryo-FIB, right?
Yes, in the cryo FIB, I mean, if the cryo condition can affect, I mean, the behavior of the silicon nitride windows or the, I mean, I don't think the stub, because in principle, I don't think.
No, well, basically stub is a metal piece, so it will shrink a bit, but it will not affect the functionality. For chips, I'm pretty sure it will sustain, but it's, let's say if you're making samples, so they're like, what we have is windows. So for windows, it's not an issue since you're preparing a lamella, and the membrane is very robust, so it will not affect the membrane because we're heating to plus 1800 degrees. So I'm pretty sure it will withstand the stresses if you go to minus 100 to 200.
Okay. Yeah, very interesting indeed. Thank you so much.
Yep. Thank you.
Okay, thank you, Ellen. Now next up will be Maria Varela. Maria, are you there?
Yes, I'm here. Thank you, guys.
Nice to hear you.
Yes, it's so good to hear you. I hope you're all doing great.
Yes, thanks. I hope you also doing well.
Yes, luckily we are not allowed into the lab, but looking forward to getting back and actually have lots of new ideas after hearing you now.
That's good.
So yes, I have just one clarification and two questions, okay? The clarification is, so I understood right, with this FIB stub, you actually mount the lamella flat on the chip, right?
No,
not
no,
at
no,
45 degrees.
No. So I will move back to the. So basically, on the flat side, we put the sample, and the chip is placed on the 45-degree side.
Yes, I know, but then the lamella on the chip goes flat.
Lamella it's the same approach as before. So we put lamella on the chip on the certain angle of 9 to 10 degrees to be able to access both sides when you do the milling. So I will.
Okay, so 9 to 10 degrees. I mean, I'm worried about tilting single crystals on the microscope. Finally, you know.
Yes, you can actually tilt. Basically, in order to get back to centric, to the zone axis, you can tilt. Basically, you need to tilt back using the beta axis, and then you having your let's say tilt range is totally possible.
Okay, excellent. Now the two questions are the following. Now I see that you can actually mount two chips simultaneously on the same stub, right? So you could prepare two samples, ideally, if you were interested in the same material or whatever.
It's slightly different actually. This FIB stub is indeed you can place two chips, but currently in the current geometry it's meant for geol chip and it's meant for FEI chip. But potentially we can change. I also was thinking about that we can change maybe the geometry of the FIB stub such that you have two chips, and in this case you save time on the additional. You don't need to do additional vent.
Okay, fine. And then the final question is, do you have any tips for like, I mean, how easy is it to do some final cleaning once everything is done and just before removing the sample from the FIB? I mean, how can you just achieve the final surface cleaning, all right, with this geometry?
You mean
you know that we're actually worried about cross sections and you know.
Yes. But you're talking, you mean in the FIB or outside like nanomill?
In the FIB.
But well, in the FIB it is possible to clean. So at least you usually, well, in the FIB I'm using like 2 kV, but if you have a better FIB, maybe you can go to 1 kV and try to basically do the polishing there. So maybe I didn't understand the question properly.
No, that's good. And then are the chips compatible with the nanomill as well, since you mentioned that?
Well, I know, let's say we don't have any solution, but I know our customers from South Korea, from SKKU, they're actually using the chips in the nanomill. So basically you can create, I guess, a special holder for those chips, and you can actually clean them in the nanomill.
Okay. All right. Okay. Thank you so very much. Take a lot of care.
Yeah. Thank you. You too.
Okay, and we had another question from Justinas. Justinas is now online. It was also a question about final sample milling. So,
hello everyone. Do you hear me?
Yes.
Yeah. Okay. Thank you for a very nice presentation. I have also a question related to the final milling. So when I do final milling on my traditional FIB samples or FIB samples on MEMS chips, I use a bit different approach, but I'm really impressed with your approach. I usually like to see, while cleaning final steps, how it evolves in SEM. But from your geometry, I still don't know. You cannot see how the sample surface evolves during final cleaning on both sides. Do I get it right? I mean, you can see from one side, but from another side, you are kind of doing blind.
Yes. Yeah, so in this case, so well, we have again a small video from Technical University Darmstadt. So I can, in a second, I will play it, but overall, you're right. So we only can observe the surface, the top surface. But the thing is, the approach is, so you define the conditions for the top surface, and you do the same milling and conditions on the bottom. And just to show how it works.
Okay.
So this is the milling on the chip.
Mm-hmm.
So, but in this case, you do the same approach. You tilt back and forth and define the region of interest and mill from one side and the other side.
Okay. Okay. Or you can flip the chip around. But no, you cannot do it.
Well, I never tried actually.
Actually, I have just one extra question which came to my mind. You was talking about prevented short circuits by extra milling the line through the chip.
Yes.
In this silicon nitride window, I'm just thinking, why you don't manufacture the chips which have this line already?
Well, that's basically one of the ideas, but
I mean, it's not too difficult to mill the line, but if it doesn't affect overall functionality, I'm just curious.
Yes, well, I totally agree. But the thing is, it's let's say you learn while you're doing stuff. So in the beginning, we didn't think of the shortcuts issues, and then while studying, making samples and measuring the samples, it just made us realize we need to have this cut there. So okay. Yeah, and I hope we will be able to introduce this cut in the chips from the beginning.
Okay, thank you very much.
Thank you.
Yeah, all the best. Bye.
Okay, and with that, we come to the end of this Nano Talk. Thank you all for watching, and I invite you to follow us on our social media accounts, LinkedIn and Twitter foremostly, and also subscribe to our newsletter so you will always be informed if we will organize new webinars. And well, this was it. Thank you for watching and see you soon.